Good evening, friends. Welcome, welcome, welcome to the Natural History Museum of Utah and to our final lecture of the 2022 Lecture Series. We're really excited to have you with us, and thank you for joining us here in person and online. It's good to have you all with us. My name is Jason Cryan. I'm the Executive Director of the museum. I'm proud to be in this beautiful facility and this beautiful night, and for a wonderful speech tonight, or a wonderful presentation by our speaker, Dr. Pearl Sandick, who will help us illuminate dark matter as we illuminate the natural world. So before we begin, I'd like to acknowledge that this land is named for the Ute tribe and is the traditional and ancestral homeland of the Shoshone, the Paiute, Goshute, and Ute tribes. The University of Utah and the museum recognize and respect the enduring relationship that exists between many indigenous peoples and their traditional homelands. We also respect the sovereign relationship between tribes, states, and the federal government, and we reaffirm our commitment to a partnership with Native nations and urban Indian communities through research, education, and community outreach activities. So our annual lecture series is possible only with the generous support of our many amazing sponsors. And I'd like to show how we are particularly grateful to our founding underwriter, the R. Harold Burton Foundation, our underwriter, the Cultural Vision Fund, for their ongoing and longtime support of this lecture series. We'd like to thank our gold sponsors, Rio Tinto Kennecott and the M. Lazy M Foundation. Our silver sponsors, the 9990 Group and Morgan Stanley Private Wealth Management. The DiFiore Family Foundation, Paula Swanner Sargetakis and Joseph Sargetakis of Frogbench Farms, Andrea and Paul Matlin, the Nature Conservancy, and the Wolf Clark Foundation. And we're also very grateful to our community partners, the Clark Planetarium, the County Library and Viridian Event Center, Kingsbury Hall, and Liberty Heights Fresh. And finally, we express our gratitude to the voters of Salt Lake County for their approval of the Zoo Arts and Parks Fund, the ZAP Fund, which provides invaluable institutional support for the wonderful programs that we provide here on site and across Salt Lake County. So let's get right to it. Tonight's featured speaker is a theoretical particle physicist, Dr. Pearl Sandick. Pearl's an associate professor right here at the University of Utah in the Department of Physics and Astronomy, and she's also an associate dean for faculty affairs right here at the University of Utah. That's amazing, right? She's earned her PhD at the University of Minnesota, and she completed a postdoctoral fellowship in the theory group at the University of Texas at Austin and moved here to Utah in 2011. We're in for a treat this evening because I saw her last evening and she gives a great presentation. She's an amazing science communicator. She has given a TEDx talk. She's been interviewed on KCPW's Cool Science Radio and NPR's Science Friday. And she's been recognized for her teaching and mentoring work by the University of Utah with both an Early Career Teaching Award and a Distinguished Mentor Award. These are pretty amazing accomplishments. Congratulations. Pearl served on the American Physical Society, the APS Committee on the Status of Women in Physics, and as the chair of the National Organizing Committee for the APS Conferences for Undergrad Women in Physics. We're really excited to welcome Dr. Pearl Sandick.
Thank you so much. It is a real honor to be here and to see all of you in the audience here, so welcome. And I also want to say welcome to those of you who are joining us remotely. This is fantastic. So I'm very excited to tell you about one of my favorite topics, which is dark matter. So I'm a theoretical physicist, and what I want to do today is give you a little bit of a feeling about how a theoretical physicist thinks about the universe and what it's made of, and how we address certain issues like the question of dark matter. So I want to start by saying what you're looking at on the screens is an artist's rendition of a particular telescope called the Fermi Gamma Ray Space Telescope. And this is in space, orbiting the Earth, actually. And it's one of the really important tools that I'm going to tell you about that will help us see the light from dark matter, if it's there. So what is the universe made of? First of all, let's think about the matter in the universe. Now, matter is anything that has mass. if you think about all of the matter around us, all of the massive stuff around us, so that's like me and you and the person sitting next to you, and the Earth and the stars and the gas around the stars and the galaxies, all of that stuff only makes up a small part of the matter in the universe. The vast majority of it, 84% of the matter in the universe, is something that we actually don't know what it is yet. So we call it dark matter. And as I hope to convince you, there definitely has to be something there, but what it is really one of the most important questions, the important outstanding questions in modern physics. And it's something that I'm working on, as well as thousands of my colleagues around the world. So we know about dark matter. We know a lot about it, actually. Everything we know about it comes from gravitational evidence. So when you're talking about gravitation, you're talking about how things clump together and are attracted to each other because of their masses. And all of our evidence sort of looks something like this. So this is a galaxy, and galaxies have some rotation, so the objects in galaxies are rotating. So if you think about a star that's bound to a galaxy, and it's rotating in the galaxy, right? You can define a speed that it's rotating at. You can measure that, actually, by looking at the galaxy. And the reason that it has that speed is because of the force of all the stuff that's attracting it to the galaxy. Now, let me point out the force and the rotational speed. So if I just told you, if I asked you, how does the force affect the rotational speed that you would expect to see for these things, right? You might have to think about it for a couple seconds. Some of you might get it, but I think it's actually much easier to think about a different type of centripetal force. So many of you might have played with this toy or seen someone play with this toy. And now if I asked you, if it pulls harder on your ankle, does that mean a larger rotational speed or a smaller rotational speed? Anybody want to answer? Larger, fantastic. Yeah, so if it pulls harder on your ankle, that means it's going to have a larger rotational speed. And exactly the same thing is true with this galaxy. So the more stuff that's pulling on the star in this galaxy, the larger the rotational speed is going to be. Now, this was an extremely important technique in order to identify dark matter, or to show that it exists. And what you're actually looking at here, this technique, is something called galactic rotation curves. So the plot in the middle here, on the vertical axis, you're seeing that rotational speed, and on the horizontal axis, you're seeing the radius, or the distance from the center of the galaxy. Now, there's stuff inside galaxies that we can see, right? There's the stars inside galaxies. Usually those are in like a disk or something, and so that's why it's labeled disk on here. There's also stuff that we can see in different wavelengths, like maybe in X-rays. We can see that there's a clump of gas around the galaxy. And each of those components contributes to the gravitational attraction of the galaxy. But if you add up the rotational speeds that you would expect from those two components, the matter that you can see in the galaxy, it falls really far short of the measurements of what the actual rotational speeds are. So the measurements are the thing that looks pretty flat going out to really large radii. So how do we bridge that gap, right? There's one idea, which is to add an additional component of some unseen matter that gravitates. And so that's the idea of a dark matter halo that could potentially explain these experiments. So this technique, the ability to make these galactic rotation curves, to make those measurements and make these plots, was pioneered by a woman named Vera Rubin in the 1960s and 70s. The top picture of her is sort of like in her middle-aged scientist career, but I really like the bottom picture of her, which is how she got her start as an astronomer, doing research as an undergraduate student at Vassar. So hooray for undergraduate research. I hope everybody finds their passions and finds them early. Okay, so let me show you another pretty picture because I like showing pretty pictures. So this is this is a simulation of the Milky Way galaxy. And on the right, you have the Milky Way galaxy with dark matter. On the left, you have it without dark matter. And you can't see the difference, right, because we can't see dark matter just in this picture. However, when I set it in motion, what you'll find is that if you look specifically at the stars on the outside of the galaxy, you'll see that the one on the right, the stars are rotating a lot faster. So this is a really big effect. It's not like a tiny effect. This is actually like a really big difference. So what could that be, right? So this is the mystery. I want to show you one more piece of evidence that I think is really cool, which actually combines measurements from three completely different techniques. So this is something called the bullet cluster. And the bullet cluster is actually two clusters of galaxies, huge, huge objects that have recently had a head-on collision. So the three different measurements that you're seeing here are first measurements from the Hubble Space Telescope in the optical. So that's like sort of the bright spots. And those bright spots are not actually stars, they're galaxies. Those are whole galaxies. Now, when these two galaxy clusters had a head-on collision, the individual galaxies would have just flown right by each other. The second measurement is in X-rays. So this shows you where the hot gas is. If you forget about dark matter for a minute, and you just think about the visible matter or the regular matter in a cluster of galaxies, the majority of it is actually in gas. So if you're thinking about like where is all the matter in the galaxies, you might be inclined to think that it tracks where the hot gas is, right? And the map of the hot gas is what's shown in like pinkish red. So the hot gas, one clump of hot gas collides with another clump of hot gas, and the hot gas kind of gets stuck in the middle because it interacts with each other electromagnetically. So that's why it's kind of stuck in the middle, and you can even see some structures in the hot gas too, which is part of why this cluster has the name of the bullet cluster. The last measurement is weak gravitational lensing. So this is using how space-time bends to track how light comes across space-time and shows you, where the stuff that bends space-time is, so where the mass is. And what this weak gravitational lensing tells us is that the mass is actually spread apart. And if you counted the galaxies in there that make up these two clusters, what you would see is that the most mass does the same thing that the galaxies do. It flies right by each other. So this is really important to me. This came out in 2006 when I was a graduate student, and I was like so excited about it. And this picture is really important and has remained important to me for a variety of reasons, but one of those reasons is because there is no way to explain this picture without some sort of gravitating dark matter. So I think that's great. We actually have a lot more measurements too, so let me tell you what we know about dark matter. And again, all of this just comes from how it gravitates. So first of all, we have to have some explanation for the gravitational phenomena. We currently do not have a good explanation for this. Second, we know that dark matter was really critical in the formation of structures in the universe. So that means structures like our galaxy and those clusters of galaxies that I just showed you. The universe would not have formed the way it did. Those structures would not have formed the way they did without the presence of dark matter as an extra thing that clumped the regular matter together. So down at the bottom, that purplish picture is something called the Millennium Simulation, which is just dark matter. But basically, they started off with like a field of dark matter, and then they let it evolve in the universe, and this is how it ended up clumping together. And that actually looks an awful lot like what our universe looks like. We have galaxies, and we have filaments that connect them if you look on really large scales. And actually, the middle picture, the circle in 4 quadrants, that's actually an interesting thing. 2 of those are observations of where the structure in the universe is, and 2 of them are simulations, and I always forget which ones are which because honestly, like, they look the same, right? And they look the same because of the presence of dark matter in that simulation. Okay, so in order to clump stuff together, the dark matter can't be moving too quickly, because if it's moving too quickly, it's going to kind of draw stuff apart. So it has to be slow moving, or we would call that cold or non-relativistic. We also know how much there is. There are a variety of measurements now, including the cosmic microwave background radiation, that helps us understand how much dark matter there is in the universe. We know that 84% of the matter is dark matter. We also know that it was observed, like through the cosmic microwave background radiation and other techniques, it was observed to be a major component in the early universe, and it's also observed to be around today. So whatever is the explanation for dark matter had to be around kind of in all of the eras of the formation of the universe. We definitely know it can't be regular matter, and we also know that it can't have a charge. Like an electron is a fundamental particle that has a charge. Dark matter can't have a charge, or if it does, it has to be a really, really, really tiny charge. So what could it be? I'm sure you're curious about what dark matter can be, and I am too. And as a theorist, a lot of my poking and prodding actually starts as thought experiments. So thought experiments date back for centuries, but they were really made famous by Einstein, right? And the idea is that you have a hypothesis, and you try to think through the consequences and see where it leads you, what all of the consequences are. So let's start with a hypothesis. Hypothesis is that there's a new heavy fundamental particle, And when I say heavy, I don't mean like pounds or tons or ounces or even anything much smaller than that. I mean like heavier than a proton. That's heavy to me. So we have a new heavy particle, and this diagram shows you that we're hypothesizing that this new heavy particle somehow talks to the other new heavy particles. So we have 2 dark matter particles there, and we also have 2 regular matter particles. And there's this yellow star in the middle, which tells you that I don't know how they talk to each other, but I'm proposing that they do talk to each other. Okay, so there are 2 arrows going back and forth. And the reason is because if you can read this diagram in both directions, that means that reading it from left to right, you would say there are 2 dark matter particles, they somehow talk to each other, they annihilate, and in the final state, you would have 2 regular matter particles. If you read it the other way, from right to left, you would have 2 regular matter particles, they somehow annihilate or have a collision, and they create 2 dark matter particles. In the very early universe, you probably have all heard that the early universe was hot and dense, and it was hot and dense, and then today we have something that's much colder and much less dense. So the universe expands and cools throughout its life. And in terms of this dark matter picture, we can think through the consequences of what would happen to these interactions and what that would mean for what we observe today. So this is a plot that sort of helps you think through those consequences. So on the vertical axis, there's the number density. This is just like the number of dark matter particles per unit volume. And on the x-axis is a funny unit, it's a sort of funny, a funny way to talk about the time. So all the way towards the left is the early universe, and all the way towards the right is today. So we start out in the early universe, it's hot and dense, there's a bunch of dark matter particles, there's a bunch of regular matter particles. And as the universe is expanding and cooling, the first thing that happens is that the cooling wins. And what that means is that as the universe cools, these regular matter particles lose energy, as do the dark matter particles, right? But remember, the dark matter particles are heavier. And so at some point, the universe cools to the point where the regular matter particles don't have enough energy to create these heavier dark matter particles. So what happens is this reaction stops going that direction. It can only go one direction now. And the direction that it goes is the direction where dark matter is destroyed and regular matter is created. So what happens then is that the number density of dark matter particles falls off, right? Now, this goes on, and throughout the evolution of the universe is expanding and expanding, and the next thing that happens in terms of the dark matter story is that the universe's expansion becomes so significant that it becomes difficult for dark matter particles to find each other to annihilate. So when that happens, it becomes really hard for 2 dark matter particles to annihilate to create 2 regular matter particles. And then this reaction really doesn't go in either direction anymore. So whatever amount of dark matter you have at that moment, you are stuck with until today. What's really cool about this, I mean, that whole picture is very cool, right? But it gets even more cool because it turns out that if this heavy new particle has what we call weak interactions, that's one of the 4 fundamental forces, and it's massive, we already said it was massive, it turns out that you get basically the right amount of dark matter left in the universe that we observe today. That is a huge, maybe it's a coincidence, but it's a really cool fact. So we call these particles WIMPs because they're weakly interacting and they are massive and they're particles. And what this, as a particle physicist, I think this is especially interesting because it seems that cosmology is telling me that a new fundamental particle could be the solution to the dark matter problem. I mean, how amazing is it that that whole picture, that whole thought experiment just works out, right? Now, particle physicists have a whole bunch of other reasons for thinking that there might be other new particles beyond the ones that we already know about. So let me tell you a little bit about the particles we already know about, and then we'll get back to the dark matter picture. So the particles we already know about are captured by the standard model of particle physics. They are shown here in this table. There are 17 of them. Until 2012, there were only 16 of them, and then we discovered the Higgs boson at the Large Hadron Collider, which many of you probably remember. The standard model is amazing. It is a mathematically complex and beautiful thing, and it mostly works. Like every time we do a collider experiment, almost every experiment we have done has verified that the standard model works the way we think it does. The mathematics gives you some predictions, we do an experiment, we verify those predictions. So it's beautiful in itself for that reason. However, there are a whole bunch of reasons that we're pretty confident mean that the standard model is not complete. There has to be something else out there. So first of all, there's no explanation for dark matter in the standard model. None of the particles that you see here could actually be the dark matter. So that's a pretty big one. It also doesn't include dark energy, which is a totally different beast. Dark energy is responsible for the accelerated expansion of the universe. There's no explanation for that here either. The third thing is that we know that neutrinos, that's these dark green particles here, the neutrinos have masses. We have observed things that could only happen if neutrinos have masses, but the standard model requires that they're massless. The mathematics of the standard model doesn't work unless the neutrinos are massless. So that's a problem. Like, that makes us understand that there has to be something else. Standard model also doesn't include gravity. There's no way to sort of quantify that these particles actually gravitate, that these things that have mass gravitate within the standard model. It also can't explain why we and everything around us are made of matter and not antimatter. Like, how is it that there was just the right amount of matter left over in the universe to create everything we see today? And there's also some other theoretical questions, like, why is gravity so much weaker, so much different than the other three fundamental forces? So there's a lot of reasons why we know that there has to be something else beyond the standard model. And furthermore, the solution or the answer to many of these puzzles really should be addressed, or actually it makes it possible to address it if you have a theory that has new heavy particles. So from the particle physics side, new heavy particles solve a bunch of these problems or contribute to the solution to a bunch of these problems. And from the cosmology side, it also seems that a new heavy particle is exactly what you need to solve the dark matter question. So I think that's pretty compelling. It's at least a good reason to start looking around for it. So let's talk about how we look for dark matter. It all goes back to this picture with the two standard model particles, regular matter, we can call them standard model now, and the two dark matter particles. So there are all different ways that you can read this diagram. If you read it from left to right, you start with two dark matter particles. They somehow annihilate and produce two standard model particles. If we see signatures of those standard model particles, that detection technique is called indirect detection of dark matter. If we read it the opposite way, where we start with two standard model particles, we smash them together, and now remember, dark matter is heavier, so we have to smash them together with a lot of energy, and somehow create two heavier dark matter particles. That's what we're doing at particle colliders, we hope. You can also read this diagram from bottom to top or top to bottom. So if you start with a dark matter particle and a standard model particle, and somehow they bump into each other, and at the end of the day, you still have a dark matter particle and a standard model particle, if we're able to observe that bump, that would be a direct detection of dark matter. And then there's one other thing, which is basically that we have all of these astrophysical and cosmological measurements. So far, they're really, the confirmations that we've had about dark matter have only come from its gravitational evidence. But if we ever have some sort of astrophysical or cosmological measurement that tells us something about the non-gravitational nature of dark matter, then that would be what we call an astrophysical probe. And I'll talk about one of those at the end of the talk, too. So let's start with collider searches. So I can show you a beautiful picture of the countryside in Europe. You're actually seeing both France and Switzerland, and there's a white dashed line that goes through like the upper middle of this picture that shows you the border between Switzerland and France. You can see the mountains in the background, and there's a lake, and at the point of the lake in the middle of the picture, you would be able to see downtown Geneva, which is kind of obscured by the water jet, which is a major feature there. So the ring here, the circle, is a 27-kilometer, 17-mile circumference ring that marks where the LHC tunnel that the beams circulate in is. So you wouldn't actually see it. It's about 300 feet underground, underneath all of this farmland. And there's an accelerator complex, and then there are also several collision points, and we place the experiments at the collision points. So I'm going to talk about two experiments just very briefly. The first is ATLAS, which is located sort of near the CERN accelerator complex, and the second one is CMS, which is like as far away from that as you can get. So what does the LHC do? The Large Hadron Collider collides protons. Now, you didn't see proton on that picture of the standard model because a proton is not a fundamental particle, it's a composite particle. So protons are actually made of quarks and gluons. So what's shown here are protons, which on average have 2 up quarks and a down quark. So the LHC wants to smash these protons together and create an explosion of particles coming out and just see what flies out of that collision. Now that's really hard to do. So if you try doing one proton on one proton, you're not going to be lucky very often. So what they actually do is create bunches of hundreds of billions of protons and collide one bunch of hundreds of billions of protons with another bunch of hundreds of billions of protons. And in order to do that, they have to focus those beams down to about the size of one human hair in the collision point. And then, whammo, if you're really lucky, on average, you get about 20 collisions every time the bunches collide. So 20 collisions actually is a lot of stuff happening at the same time. And so you need some very serious particle detectors to be able to figure out what is coming out of those collisions. So the 2 detectors, as I mentioned, one is CMS, the compact muon solenoid. CMS is compact in that it is only about 5 stories tall. You can see a little person down at the bottom for reference. Atlas is a toroidal LHC apparatus. And there are some people down at the bottom for scale there too. It's about 7 stories tall. But you can see that they both they have some things in common, right? They're both kind of oriented along the beam axis. So they're concentric detectors around the beam axis because that's the beam comes through and then there's the collision. And each of the different components of the detector is designed to detect a different phenomenon, a different type of thing that's coming out. So that's what a lot of the color coding is. So these 2 experiments have been running since roughly 2008, right? And they've been upgrading the beam to make more collisions, to make it higher energy, and they've upgraded the detectors a little bit too to accommodate that. Creates a tremendous amount of data, and most of that data is analyzed by machine learning these days, but it's just a fantastic enterprise. And something really exciting happened that some of you may have heard about last week. After 3 years of a shutdown for upgrades to the magnets and the beam and to the detectors, after 3 years, they restarted the LHC last week on April 20th, which was very exciting. And they actually now can operate at higher energy and with more collisions per second. And now if we're talking about taking 2 protons and smashing them together to make a heavier new particle, more energy and actually more collisions per second, both are going to go in the direction of helping you see things that you were not previously able to see. So that is extremely exciting. So this is a picture of the control room, or a control room at CERN. And I don't know if anybody notices anything strange about this picture. I would say this is an unfortunately typical group of particle physicists. This is just one of the pictures that was on the CERN website. I did not choose it specifically for the representation. Really, the lack of diversity here is difficult to ignore. It is palpable, right? And this happens from time to time. And I just want to say that there are a lot of us who are working really hard to change that and to make sure that this is a more inclusive field and that everybody who wants to is able to join in the fun. All right, so back to dark matter hunting. So let's read this diagram now from bottom to top. This detection strategy is called direct detection. And if you're going to have some standard model particles sitting around, essentially waiting for dark matter particles to bump into them, you want to have some idea of how often that's going to happen, right? So there are dark matter particles flying through us all the time. In fact, there are a whole bunch of them in this room. They're flying through you. If everybody hold out your finger, flying through your fingernail every second, there are about 100,000 dark matter particles. On average, you will have about 1 in your coffee cup. So they're all around us. They're not the only thing flying through us either. But how often do these dark matter particles flying through us bump into the nuclei in our bodies? That calculation has been done. It's not very often. But if we're going to build a detector, we should really figure this out in detail. So I only have one equation in this slide, but I do want to show you an equation because I am a theoretical physicist. Okay, so this is the equation that tells you the scattering rate that you would expect in one of these experiments. So I'll go through the pieces. The first piece is the flux of WIMPs coming through the detector. So that depends on the density of WIMPs, or density of dark matter particles around the detector, a speed that they're all moving at, and the mass of the dark matter particles. Of course, the dark matter particles are not all moving at the same speed. They have some distribution of speeds or velocities, so that's this piece. And then the last piece over here is actually the particle physics part. Given some dark matter model, what is in that yellow star? So what is the probability that a dark matter particle is going to interact with a nucleus? And then when you have your detector, not every dark matter particle that bumps into a nucleus is going to create a signal that's big enough to see. So it has the scattering, the dark matter particles have to come in with velocities that are big enough to produce an observable signal. So you integrate over all of that, and what you get is a differential scattering rate. So this is the counts, the dark matter counts in your detector per ton of detector material, per year of operation, per keV of recoil energy. So the big part here is per ton, a ton is a lot, per year, a year is a long time, and the numbers that you get out of this equation are like 1 or 2. So you're really waiting for a very rare event, and if you're going to look for a very rare event, you have to make sure that you're not seeing any other events that could be much more common. So in order to do that, we build the detectors very deep underground in order to avoid those backgrounds. They have been building detectors that do roughly this for a couple decades now, and they are all over the world. So to be underground, you're usually going to either be in a mine or you're going to be under a mountain. Some of the ones that are close to here are the Homestake mine in South Dakota. So Homestake mine was actually an active gold mine until very recently. In fact, parts of it are still active for some mining purposes. But they have a huge science cavern. So you can take the elevator down a mile and go into the science cavern, which I have done, and it was amazing. I've actually, for a theorist, I've been in a lot of mines. I've also been in the Sudan mine, which is in Minnesota, another science mine that as a tourist, you can actually go in the Sudan mine, or you used to be able to anyway, which was pretty exciting. But we took a science tour of all of the experiments that were down there, because it's not just dark matter experiments, there are also a lot of neutrino experiments that are in these mines. Now, across the world, there's Snow Lab in Canada, there's Gran Sasso National Lab in Italy, Jinping Lab in China, and there's even dark matter, there were dark matter experiments at the South Pole. So anywhere you can get under a large overburden of stuff to protect you from all the other stuff that's flying at your experiment, that's a good place to look for dark matter. So what is the current progress here? What these experiments are finding, so far, not much conclusive, but this plot is really kind of a summary of the state of the field of direct detection of dark matter. So on the vertical axis is this dark matter nucleon interaction strength. The stronger that interaction between the dark matter and the regular matter, the more easy it is to see it, right? So anything above these sort of sensitivity curves would mean a dark matter interaction that's too strong. We would have seen it by now, so those parts are excluded. I don't know if you can see the gray shaded region is like the overall excluded region. Now, on the x-axis is the dark matter mass in some funny particle physics units. So just for reference, 10 to the 0 is 1. That is the mass of a proton, more or less, is 1 GeV. And so that's basically under the little xenon XE is right about 1 proton mass. So this plot goes out to quite heavy dark matter masses. But again, it is heavier, more or less heavier than a proton. There are a couple other things that I want to note. So the solid lines are experiments that have already been done, and those are, everything above those solid lines is excluded because we didn't find dark matter there, but we did find some interesting hints. The dashed lines and dotted lines are projected sensitivities of the next generation of experiments, and I'll say a little bit about those in a minute. The blue region is something that is labeled the neutrino fog. And until last year, approximately, we didn't call it the fog, we called it the floor. Because, once you get to cross sections, once you get to interaction strengths that are that small, you're looking for very rare interactions. And it turns out that if you're sensitive to very rare interactions, you're also going to be sensitive to neutrinos that are scattering in your detector. Neutrinos are also flying through us right now. They're just like dark matter in that they interact very rarely. And so eventually these experiments are going to start to see neutrinos, which is cool for neutrino physics and maybe a little less cool for dark matter physics. So we call it the fog, though, because now we have techniques to allow us to go below the neutrino floor. The other thing I'll say is that the region that's plotted here, it looks like all of the measurements fit nicely in here, but there are actually physics reasons that this is the region of interest, that these that these interaction strengths are of interest. It's highly likely that whatever the dark matter is, if it's a WIMP, it is somewhere on this plot. So we just have to figure out where. Now the dashed lines and the dotted lines are the projected sensitivities. The future experiments that I listed here, LZ is the Lux Zeppelin experiment. That's going to be located in the Homestake mine, and I think it actually started commissioning already. Panda X 4-ton is in Jinping Lab in China. Xenon N-ton, I believe the N is going to turn into a 7. Xenon N-ton and DarkSide are both located in the Gran Sasso National Lab in Italy. So we have all of these to look forward to. They're very complementary in that they're like using slightly different techniques to look for the same thing. So it would be great if dark matter lives in one place on this plot, that all the experiments that are sensitive to that place would all see it, right? So that's what we're looking for. Now, these experiments are all like either under construction or ready to go, and so we actually expect to get to the neutrino fog like in the next 5 years, which is amazing, right? Like it took us decades to get down halfway on this plot, and now we're really in the home stretch here. So it's really exciting. And once we do get to the neutrino floor, again, there are different strategies. So the coming attractions, you'll notice that the sensitivity curves all kind of go up towards the left side of the plot. That's because less heavy dark matter requires different techniques, and people are working really hard on that. I mentioned that there are some hints. That's something that we are going to continue to investigate, although right now it seems like every time there's been a hint of a dark matter detection in one of these experiments, there's another experiment that says, no, we looked there and we didn't see it. Going towards the neutrino floor on a timescale of 5 years is amazing, and then after that, a really important detection strategy is going to be directional dark matter searches. If you really want to tell what came into your detector, whether it was dark matter or a neutrino, the big background for neutrinos is solar neutrinos. So if you know that it came from the direction of the sun, it's much more likely that it's a neutrino. So super exciting stuff to look forward to in direct detection. Now, indirect detection is something that's sort of familiar already because we already talked about 2 dark matter particles annihilating and producing regular matter, right? And I said that that hardly ever happens today, but if you have a big enough clump of dark matter, a real concentration of it, it can still happen today. So the idea here is that you're looking for the end products of dark matter annihilation. And one thing that I think is really special about this is if this happened in the early universe, then it's going to still be occurring today. And this is a link between the physics of the present day and the physics of the very early universe, which it's just really, I think, special to be able to make that link. Now, it's not always a direct link, and there are a number of challenges to this type of observation. The biggest challenge is you're basically using telescopes to look for stuff coming from our galaxy or outside our galaxy, and usually there's a whole lot of other things in our galaxy or outside of our galaxy that could make signals like that. So, we have to know how much dark matter there is and where it is in order to make a good prediction. Then if dark matter annihilates to some standard model particles, like an electron and a positron, you have to worry about how those are going to move around in the galactic magnetic fields before they get to our detectors. It's also, as I said, really difficult to make sure that what you're seeing is not just something that we expect to be in our galaxy. But the good news is there are tons of telescopes and other experiments that are looking for stuff like this, and so we can make a really coherent picture now, which is fantastic. So I'm just going to give you a summary of some of the interesting indirect detection targets. So this picture that you're looking at, first I'll talk about the picture and then I'll talk about the targets. So the picture is actually 2 things superimposed. The oval shape with the white areas on it, like white dots and white clouds, that's our galaxy. So the way you would read this is looking towards the center where the bright yellow light is, that is the galactic center. Looking out in the horizontal bar part, that's the disk of our galaxy. And so if you're looking in the disk of our galaxy, you can look across the sky all the way around, back and forth across the picture. And you notice most of the light is coming from that disk. That's because most of the regular matter sources of gamma rays, which this experiment is measuring, most of the sources of gamma rays are around the stars, and the stars are in the disk. The other thing is, if you want to look out of the galactic plane, right, away from the spiral arms of the Milky Way, you'd be looking up and down on this plot. Now, the sort of spherical rainbow in the middle is where we expect the dark matter to be, and the brighter the color, the more dark matter we expect to be there. So you can see most of the dark matter is clumped right at the center of the galaxy. So you might think the galactic center is a really great place to look for dark matter. And it is. However, there's also a lot of regular matter stuff at the galactic center too, and so it can be really hard to disentangle what is the regular matter expected contribution and what is the extra bit that might be coming from dark matter. I will say there is actually an observation of excess photons coming from the galactic center in the gamma ray range, and it's been known for several years now, and it looks like dark matter an awful lot, but there are also people who say it looks like pulsars an awful lot. And so we're really waiting in the next few years. There are some experiments that are going to help disentangle that, because they would be able to pick out those photon sources of, if they are pulsars, they'd be able to pick those out and give us a much better idea of what the expected contribution from pulsars is. And then we can say, oh, is there any left over that could be dark matter? At the moment, people are using really interesting techniques to try to disentangle it, but I think this is also going to take more observations. Okay, so that's the galactic center. Then you can think about, well, you can see that rainbow extends out of the galactic plane quite a lot. And out of the galactic plane, there's a lot less regular matter, and so there's a lot less photons from like regular astrophysical sources. And so that is a really interesting strategy too, and there are different types of telescopes that are more sensitive or less sensitive to that. You can also think about galaxy clusters, sort of outside of our galaxy. The last thing I want to say, though, is dwarf satellite galaxies. So dwarf satellite galaxies are really interesting because they're like mini galaxies. They're kind of nearby the Milky Way. So these things are maybe like a fraction of a % of the size of the Milky Way in terms of mass, but there's not much in them that could mimic a dark matter signal. So when you look at those galaxies, they have maybe anywhere from like dozens to a few thousand stars in them, and we can look at them with telescopes and track the motion of the stars to map out where the dark matter is, because if we know how the things move around, we can know where the dark matter is. So you can map out the dark matter in them, and then you can see if there's any extra photons that are, because we don't really expect, especially in the gamma ray range, we don't really expect any contribution from the regular matter in dwarf satellite galaxies. So very cool and a super active area of research right now. The last technique I'm going to talk to you about is what I'm calling astrophysical probes. There are many, many different types of astrophysical probes. I'm actually going to talk about a way that dark matter could have affected the very first stars to form in the universe. So if we think about what a star looks like, a regular star like our sun, it has fusion going on in its core, and the fusing hydrogen into helium and then eventually more heavy elements results in a deposition of energy in the star. Stars are mostly, especially in the very early universe, are mostly hydrogen and helium gas. So the fusion is depositing energy in the gas, and the gravity is pulling the gas in to the center of the star, and it's actually in balance. Like, that's what determines the size of a star. However, if you think back to when the very first stars formed, it turns out that they would have formed at the very center of the dark matter halos. And just like I showed you in the previous picture, at the center is where there's the most dark matter. And it turns out that if you calculate how much dark matter annihilation would get stuck in the hydrogen and helium gas, the dark matter annihilation itself can actually power the star. This is an idea due to one of my colleagues here at the University of Utah, Paolo Gondolo, as well as Katie Fries and Doug Spoliar. And it's they thought of this, I think, in 2008, and it's been a real magical time calculating all of the consequences of this, because this happened long ago in the universe. Some of them might be around today. Some of them might have collapsed, ended their lives as black holes. But what's interesting about this is if you have this picture on the right, dark stars are fundamentally different than regular stars. They're going to be bigger, they're going to be puffier, they're actually colder, but they emit more photons. So for all of these reasons, they would look very different than a regular star. And that leads to tons of different detection possibilities, and also different ways that they could have affected the evolution of the universe and the stars that came after them. So there are three things that I will say about how we detect these guys. First of all, there are super interesting cosmological and astrophysical signatures, including how they could have affected the cosmic microwave background radiation. The second thing is, these dark stars could have been huge, millions of solar masses even. And that actually can help solve another type of puzzle, which is that we have a supermassive black hole at the center of our galaxy, and actually most galaxies have a supermassive black hole at their center. By supermassive, our supermassive black hole is 4 million solar masses. And it's kind of been a little bit of a puzzle in astronomy how you create a black hole that's 4 million solar masses at the center of a galaxy. And so these dark stars actually would provide the seeds for supermassive black holes, which is kind of remarkable. The other thing is they could be seen directly by a very new space telescope that launched a few months ago. So you might have heard of JWST. This is a picture of it sort of preparing for launch in the launch facility. It does not look like a telescope because it is all folded up. And the reason that it's folded up is so it can be stuck inside the cone that goes on a rocket and blasted off into space to its final landing destination, which is about 1 million miles on the other side of Earth from the sun. So I want to show you a video of how it gets from looking like a squozen up little folded thing to how it starts to look like an actual telescope. Oh, I missed my chance. Oh no. Sorry, not my computer. Let's try one more time. So this is its folded up shape as it arrives at this place that we call the Lagrangian point 2. And it has this whole sequence of unfolding that if you imagine the scientists who thought of this and then the engineers who helped build it, this thing is huge. And you can't exactly test it, all of this mechanism, on Earth because we don't have an environment that has this type of gravity in which to test this. So these huge arms come out. Now, in order to operate this telescope, it actually has to be extremely cold. So any kind of heat from the sun would affect its operation. So what you're going to see come out next are some arms that are going to help support a sun shield. So this is this silvery thing that's coming out. And it's not enough just to have one layer of sun shield. You have to have something like 5 layers of sun shield to make sure that the actual telescope mirror stays cold enough. The mirror itself is the gold part, and you can see that it's not one mirror like in a typical telescope that you would think of. It's all of these little segments. And the little segments together have to be sort of coordinated and focused. And they're not done yet. You'll see a couple more flip out to the sides. But all of those mirrors, the individual components, make up something that's about 21 feet in diameter. There's one wing and one more wing. And all of that allows this telescope to see farther back in the universe than pretty much any other tool that we have to look for individual objects like this. This thing is a marvel of modern technology. And it launched on Christmas this year, and it was basically a whole bunch of scientists holding their breath for like a whole month throughout that whole deployment sequence. And then I remember all of my friends on Facebook and Twitter were like posting pictures when they actually started to see images that they could align in all of those different mirrors, and it was just super exciting. So amazing. I mean, James Webb Space Telescope, the Space Telescope, as well as all of the other techniques that I've shown you, they're not only for dark matter, but it is really cool that JWST could help us see something like a dark star. Okay, so I have talked about a lot of aspects of detecting dark matter, and between all of the search strategies that I talked about, we are basically going to get really interesting new information in the next 5 to 10 years. Who knows what we will find, but we'll learn more about dark matter, and we will also learn more about how it talks to standard model or regular matter. So if dark matter is a WIMP, we should see the evidence start to pile up, which I think is really cool. And if we don't see that, then what could it be? So if not WIMPs, then what? I've spent a lot of time talking about WIMPs and how we see them. And I would say, do not worry, we have plenty of ideas. So this is a cartoon, but it is true in that the range of masses for potential dark matter explanations span 80 orders of magnitude. Now, an order of magnitude is a factor of 10. And if you think about the difference between the size of a proton and the size of the Milky Way galaxy, that's only 35 orders of magnitude. So 80 orders of magnitude is like almost incomprehensibly huge. It is a huge array of different ideas for what dark matter could be. So this talk I focused entirely on this range that I highlighted in green here. It's a very small part of this whole picture, and there are different detection strategies for all of these different mass ranges. So I just want to remind you that a theorist's job is to look at what we have in front of us, right? Do our best to describe nature, and then propose ways to test it. And we have a lot of different ways to test it. It is a super exciting time right now. Okay, so I want to leave you with a message that this is an incredibly active and rich and creative field, and a really fun one too. I also want to leave you with this quote. So the dark matter enterprise started about 90 years ago with the observation from Fritz Zwicky of clusters of galaxies. And, Fritz Zwicky said, there's something funny about how the things are moving in these clusters of galaxies. And then decades later, Vera Rubin actually modified a technique and honed a technique that allowed us to not only observe it and observe something funny in one galaxy, but in a whole bunch of galaxies. And the more times we said, oh, that's kind of funny, the more confidence people had that there's actually something there. And then we collected more evidence, right? So with all of this new experimental data that we're expecting, I am really hoping that we're going to find at least one funny thing, and hopefully many funny things. And whether it's a WIMP or something else entirely, I am very excited for the future of dark matter. Thank you.